How does virtual memory cause C++ segmentation faults? Imagine trying to open a door that is locked or doesn't exist. That is similar to what happens when a C++ program encounters a segmentation fault. But what causes these faults? Today, we're going to uncover how virtual memory plays a role in these crashes. When a C++ program runs, it doesn't directly access physical memory. Instead, it uses virtual addresses. These are like labels on boxes that the operating system translates into actual locations in physical memory. This system keeps programs isolated so they don't interfere with each other. It also protects certain areas from accidental or malicious access. Now, if your program tries to access a virtual address that isn't mapped to any physical memory, the hardware raises a fault. This is a signal that your program is trying to do something it shouldn't. For example, dereferencing a null pointer points to address 0, which is usually unmapped. Trying to read or write there causes an immediate segmentation fault. Another common cause is accessing memory after it has been freed. When you free memory in C++, the operating system marks that space as available. If your program still tries to use it, the virtual memory protections prevent access, leading to a segmentation fault. Buffer overflows are similar. Writing past the end of an array can overwrite protected memory regions, causing faults. Stack overflow is another issue. If your program uses too much stack space through deep recursion or large local variables, it can exhaust the reserved virtual memory for the stack. When that happens, trying to access beyond the stack boundary causes a segmentation fault. Modifying read-only memory is also a common cause. String literal and code segments are marked as non-writable in virtual memory. If your program attempts to change them, the hardware stops it with a fault. Understanding how virtual memory enforces access rules helps you see why these faults happen. Debugging involves checking if pointers are valid, ensuring proper memory management, and avoiding illegal array access. Tools like debuggers can pinpoint the exact instruction causing the fault. Memory checkers like Valgrind can detect invalid memory use. By knowing how virtual memory works in relation to your C++ code, you can prevent many segmentation faults. Always verify pointers before use, manage memory carefully, and use safe programming practices. This way, you'll write more reliable programs and avoid those frustrating crashes caused by virtual memory violations.